Hello, I'm Fotiou Dimitrios. I'm an electrical computer engineer and PhD candidate here in Aristotle University Thessaloniki. Today I will present you image analysis for wildfire events. Wildfire image analysis is vital for rain detection, real-time monitoring and damage assessment by using satellite drone or thermal images. We can track fire spread, support emergency response, and improve prevention strategies, ultimately protecting lives, properties. Our presentation will cover the following. First, we will delve into general forest fire computer vision tasks. Then we will see some focus more on to the rest slides, to the segmentation analysis of images. And we'll see some classical segmentation approaches. Then we'll go to deep learning strategies for segmenting fire as well. And finally, we'll see some real-world implementation issues we face when we implement this model in a real scenario. There are primarily three main tasks for wildfire image analysis. Namely classification, object detection, and segmentation. Classification involves classifying an entire image to a specific category. For wildfire analysis, this could mean that determining if an image contains fire or if it contains smoke or not. There might be, except for binary classification, there might be many classes for an image. For example, we can say that an image has both fire and smoke. However, this is just a very simple task. So the next task is more complex is detection, object detection. This can be significantly more useful than classification for fire management, as actual position of the fire or smoke can give a clear understanding of the threat level and enable targeting firefighting efforts. And support real-time decision-making for evacuation plan, for example. Apart from fire smoke, we can see here an example of person fire detection. This is also an important task for us, especially in natural disaster management. We can detect the persons, so we could actually count how many persons are in the critical area, and so we can plan the evacuation strategy. The final task that we will focus in this presentation is semantic segmentation. This is most granular form of analysis, semantic analysis. They don't target the object feeders roughly through a bounding box like the object detection, but capture accurately. They reshape the image. So we actually classify every pixel of the image. This can give us even more information about how big is the problem fire. Actually, for example, if we capture the exact shape of the smoke, we can estimate other things like the wind, how the wind, what the wind directs, so we can understand where the fire may spread. Now we'll proceed to some classical image segmentation techniques. The first one is very simple, it's image thresholding. One of the simplest, most fundamental techniques. This method is particularly effective when the image contains an object having a homogeneous intensity and the background with a distinctly different intensity. Think of it as separating light from dark areas. The concept is straightforward. We define a threshold. The pixels of density that are above that threshold can be detected as fire. Here we see an example. We transform the image to grayscale. Then using a threshold 205, we can extract the fire very accurately, the fire segment. However, here we see some examples where this technique gives wrong results. for example, in the first one, we have the sun that is very bright, and this approach segments the sun, which is not our object of interest. And in the second, which is even more important and wrong result, we can see that we have a fire, but because the sun is more bright than the actual fire that is behind the dense smoke, we can find the actual fire, but again we segment the sun. The second acid strategy is region growing algorithms. This method starts with a small niche area called seed selection. This may be some points or maybe that are manually or automatically selected. Then we have some criteria that on this original points we append the neighboring pixels. This criteria may be the difference in intensity or the texture. Finally, then we have the actual algorithm that appends these neighboring pixels. They may append 4 or 8 connected pixels based on the similarity criteria. Then we have we need the stop condition. For example, if we set a maximum region size, or maybe if there are no other candidate pixels. And the final, we may have another, this optional, we have a post-processing algorithm that after we create the two areas, the fire and non-fire, for example, it may, with some statistical algorithms like Raster, we may discard points that are irrelevant. Okay, now we'll proceed to the main, to the core of this presentation, to the deep learning for fire and smoke segmentation. First, we will see some core concepts, the overall, at least. The most fundamental operation in deep learning, of course, convolution neural networks. Convolution is a mathematical operation that applies a filter, also known as kernel, to an image that extracts some features. The process works like this: a small filter, typically a square matrix, slides over the entire image. At this position, the dot product of the filter and the overlapping image values are computed. The result of the computation forms a new process image, which we call feature map. This feature map highlights where the specific features of the filter is designed to detect. For example, in here we have a filter that can detect the edges of the image. The second concept is the vision transformer. This is a more state-of-the-art neural network building group. The vision transformer originally came from prominence in the natural language processing. The key insight was that the Fotiou transformer applied directly to a sequence of image patches works exceptionally well on image classification, simulation, and object detection tasks. Instead of processing individual pixels or a small convolution windows, vision transformer breaks down the image into smaller non-overlapping patches and processes them in sequence. Here, the core concept of the vision transformer are the self-attention mechanism, which computes a weighted sum of the input data. More specifically, the weights are computed based on similarity between the input features. This allows the model to dynamically weight the importance of different parts of the image relative to each other, enabling to capture long-range dependencies and global products. We'll see an example in the next slides where this specific concept is important. The final concept is how we evaluate our algorithms. The main metric we would use is the sectional union, which is the overlap between the predicted area and the ground truth area. For example, here we can see that in the second image, the green is the ground truth, and the red is the predicted, because the predicted has a small 40% overlap with the ground truth, and the second, which has a bigger overlap, is 85%. Now we proceed with some deep learning architectures. First, we have the unit architecture that actually takes its name from its shape. The network consists of some quadratic path to capture context, the symmetric expand path that enables precise localization. This means that in the first, we reduce the spatial resolution, and we get some semantic information, semantic features. Then we want to increase the space to use this semantic information, and at the same time increase the resolution to create a high quality segmentation model. However, this model is not primarily for real-time applications because, except for it has many parameters, it also has high memory demand because these shortcuts, of course, need to be saved in the memory. And actually, the first shortcuts have high demand in memory because the resolutions are higher. Then we have a more statistical approach to the BiSnet that I forgot to say that actually the overall architecture is not easily parallelized. This also is an important issue. Here we have the BiSnet that has a similar logic with the unit. We have a path that actually captures semantic information. This means that we have more evolution process. We have larger strides, we have maximum layers that reduce the spatial resolution, but at the same time they capture longer more semantic information. And we have a second path that actually have smaller strides in the evolution and can capture more local information and keep high resolution high. This particular model, one advantage is that the two paths can be parallelized. So this could be used in real-time application. This is the architecture of the BiSnet. Then we have a model that's based on BiSnet. It's an advanced BiSnet. PIDNet features the three branch design. It has a proportional that is similar with BiSnet's path that actually have high resolution and captures global information. We have the integra path that actually this reduces the spatial resolution but has high semantic information. But here we have an additional path, this addition to this model, and the derivative path. The derivative path try to capture the boundaries of the object. So this technique is similar to the is inspired from the PID controllers, where there is the proportional integral and then derivative controller. And the derivative controller here captures actually the high frequency signal of the input impulse. Here is the actual the overall shape of the AIDA architecture. Then we have a model that have worked on the AICET2025. This is again similar with the BiSnet. However, it has an auxiliary branch to the existing BiSnet branch. The key here is that this auxiliary branch is designed to improve semantic accuracy without slowing down the execution. A unique aspect of this auxiliary branch is that it's trained using a genetic vessel network. This allows it to generate RGB-like segmentation maps, which are adept at capturing additional semantic information. Essentially, it learns to produce outputs that look very similar to the ground truth, testing the models at the starting of the signal. That research and training was, of course, a discriminator. This discriminator validates the output of the auxiliary branch. By learning through adversarial loss, the auxiliary branch is pushed to improve the semantic feature extraction, make it more robust and accurate. Here's the architecture of the output signal. And now we go to multimodal segmentation. Start with a similar modality example, except for SIM as the input, we can add additional channels that will boost the accuracy in our tasks. Now, specific task is fire segmentation. Without any additional information, just from the RGB, we could transform the RGB to HSV transformation through HSV transformation. And we can calculate from that the saturation channel, which actually highlights as you can see here, the 5 features. Then, if we concat this information with RGB and pass it to the model can actually have a greater accuracy because from the input to highlight the important features we want to detect. However, this is not actually a model because all the information is extracted from the RGB channel itself. We could actually use more sensors to achieve a better accuracy. In real scenarios, signal modality may not be detected. Fire may be hidden below a smoke, for example. So we could use infrared, a spectrum that is sensitive to heat sources and is sensitive to some gases like smoke. So it actually can see through the smoke. So if we use RGB, we can detect the visible fires, but we can also detect the smoke. And if we, in the same time, we use using the infrared, we may not detect smoke, but we detect even the visible and non-visible fire that is below the smoke. So if we combine these two, we'll have, let's say, the optimal input for a neural network. There are 3 main strategies in order to fuse this model inputs. The first one is the diffusion. This approach concatenates the 3 RGB channels with the infrared to create a unified quality input. The network then processes all the information together, like one input. However, this may have some problems because the big intense features of one modality may suppress the other smaller features of the other modality. A better solution is the intermediate fusion that we prefer to use. Here we have a small portion of the model that processes independently each modality. So in this step, the important features are highlighted in order to avoid this situation where small features are suppressed during concatenation in the early areas. And then we have the rest model that can process the rest concatenated features. And then we have the last strategy, which actually performs the worst of the 2, is the late fusion, which actually have 2 independent models that actually process each modality independently. This has 2 problems. One, we have 2 whole models process which requires double the memory usage, which doubles the memory usage. In the same time, we don't let the features to interact each other from the modalities because we only concatenate the final masks. Here we have a model that we developed in our lab, which is based on AIDA, but it uses intermediate fusion to actually fuse the RGB in the infrared spectrum in order to detect to segment concurrent, fire, and smoke. The key concepts here are that we have two small models in the start that highlights the features from each modality. Then we have the 3 months of the AIDA, the proposal, the table, and the detailed path. However, we added other small branches that each one process independently the modality throughout the model. This is actually like using an intermediate late fusion at the same time, and they take advantage of both fusion strategies. The final addition that we should refer is that we use some transformers because the original net have only convolution layers. We add some transformers in order to capture log rate dependencies. This is especially important because when we want to segment both fire and smoke, if the model can easily segment fire and smoke, smoke can actually give an insight in the model where the fire would be in the image. So this log rate dependencies which actually help this concurrent task of fire and smoke segmentation. And here we have some comparison of state-of-the-art methods. We can see that the our model can actually achieve much higher accuracy from single AIDA with single modality, RGB or different, and even can actually surpass and be better around 15% from the early fusion of the single AIDA technique. And here we actually have a small number of parameters. We may have a higher number of AIDA. However, the difference is small, and we actually have a much higher accuracy in metrics of MIU. Now about the final step of this presentation, we go to the summary of the implementation challenges and you refer to the domain shifted optimization. We need to have in mind when we implement these models in a real world scenario. One of the main challenges in natural just function, particularly with deep learning models, domain shift. Deep learning models heavily rely on large labeled data such as training. However, obtaining and annotating such data is time-consuming and costly. And in some cases, it's not even possible. Even with extensive training datasets, models frequently encounter unseen or novel data when deployed on a real-world scenario. This domain shift occurs due to changing conditions, geography, or specific type of disaster. For example, a model trained on forest fires might perform poorly on urban fires due to different visual characteristics. Solution here would be the unsupervised fire segmentation. Unsupervised segmentation actually do exist and don't rely on labeled datasets. However, without any prior information about the objects of interest, they often struggle to achieve the desired clustering and accurate segmentation. They are not able to understand that they want to detect fire, for example. To address this limitation of our supervised methods and the challenge of the massive, our research explores prompted fire segmentation. This innovative approach significantly improves performance by requiring minimal human input. Most specifically, we select a single image from the dataset, and from that image we select only one point. That, of course, is maybe the fire object of interest, and the rest is the background. By this methodology, involves the steps. The best is combining the raw images with a single from the annotated point, so have only one annotated point in the whole dataset. And the second step is pushing fire representations closer together in the feature space, effectively teaching the model what fire looks like based on that sync point. And the third step is creating a cluster head that separates fire in the background. Protein fire simulation will have some promising results. As you can see that the simple unsupervised simulations without any knowledge of the object feeders have around 50% magnitude, while our method can achieve 75% magnitude. The next strategy that we could employ, we are currently employing for solving these domains is the test time domain adaptation. TDA is a machine learning technique where the trained model adapts to a new domain specifically during inference or testing phase. Crucially, it does it without having access to the target labels during its initial during its training. Another traditional domain adaptation techniques. Here we have no target, no labels of the target data. Have actually no access to the source data too. We have only the pre-trained model in some dataset, and then we have the unlabeled target instances. The main three techniques that state-of-the-art methods are using entropy minimization, pseudo labels and memory bugs. The entropy minimization is actually taking the logics of the model, trying to make try to increase the confidence of the model by simple entropy minimization. Then we have the pseudo label that take the output of the model and we consider it as ground truth. Of course, this will degrade the performance of the model. To avoid this, we use some filtering that use only the part of the image that the model is very confident. And then the third method is the memory bug that we try again, we take the most confident part of the image and we create some features. And throughout the testing phase, we save these features and we aggregate this information to create a robust representation of, for example, fire instance. And based on this fire instance, we then refine the output of the unadapted model. In the final slide, I would like to say that optimization is crucial for applications that are running on the edge. That means that quite important because we often operate on limited resources on the edge devices. An edge device, for example, is a drone or a laptop base station that is on the field. And this typically base station and drones may have medium range GPUs with limited memory. In addition, the base station on the field may have concurrent information from multiple drones. So in this concurrently should process multiple images from multiple drones, from multiple cameras, from multiple modalities. And this may requires a very high optimization in order to be with all this process real time. And finally, the most important is a demand for fast response in fire detection, which can be different between, especially if we detect the fire in early stages, actually the firefighters would actually perform do their job better. How optimization is achieved? The first one is choosing only real-time simulation models. The one I present you set from the unit are in the real-time simulations. Even the ones we developed are real-time simulation models that, except for that requires small demand in memory. It's actually have paths that can be parallelized. This is very important. The second step is using quantization to reduce the floating point precision. This means that if we have a model with 12 million parameters, then instead of representing each parameter with, for example, 4 bytes, we could use just 1 byte or 2 bytes. The final specialized technique for optimization is using TensorRT, which is developed by Wicket's framework. It's this high-performance deep learning inference optimizer that can dramatically accelerate throughout the efficiency of the deep learning applications by applying various optimizations, such as layer fusion, precise and precision compression, parallelization of batches, and the most efficient mathematical algorithms of the basic DNA operations. That's the presentation. Thank you very much. If you have any questions, both local and online.